Hi everyone. In this video we're going to work on coming up with a Python code that will execute Newton's method for polynomials. And where I want to start today is considering this polynomial where I say f of x is equal to x cubed minus x plus 2. So of course, our goal here is to use Newton's method, and Newton's method has a formula that looks like this. And clearly, in order to use Newton's method, we're going to need to take the derivative, and so I'm going to write f prime of x is equal to 3x squared minus 1. So write this down in your notes really quick, and then we're going to be using this during the rest of the video, but I'm not always going to have this screen up. The idea is to show you in like a spider Python environment how it looks to write that code. So here we go. The first thing I'm going to do is define a function. So I'm going to type def fun for define a function. My function is going to be a function of the variable x, and so I just do it like that. Hopefully this font is large enough for everybody to see. And what I want this function to do is whenever I tell the function the value of my variable x, I want it to return x to the power 3 minus x plus 2. So how you do powers in function in Python? You want to do powers in Python, you have to do a double asterisk. A single asterisk would denote multiplication. And then for the derivative, I'll call it fun prime as the name of my derivative function. And so that's going to be 3 times x squared minus 1. Now, the initial iterate that we're going to use is going to be -1. And then the formula for my next iterate, which I'll call x1, is going to be x naught minus fun of x naught divided by fun prime of x naught. So hopefully you see where I'm getting this from. Again, using the polynomial we're given and using my Newton's method formula. And then if I type in print x1, then what this program is going to do when I hit run is it's going to tell me what the first iterate will be if I perform Newton's method on this polynomial, with my initial iterate being -1. So whenever I hit run, of course, it runs my little Python script, and the output here in the console is -2. And so my first iterate goes from -1 to -2. And just like I did in the previous video, I went ahead and plotted what this would look like on Desmos. So you probably remember this kind of graph from my previous video. And just visually what this Newton's method looks like is I'm going from x equals -1 up to my function, taking the tangent line approximation, which has a 0 at x equals -2. So initial iterate and then my first iterate over here. And then it looks like eventually this should converge to a 0 of my function. But we're not there yet. So the next thing you might do naturally is say, well, if I want to get the second iterate and not just the first iterate, I could do something like this. Just repeat the Newton's method formula and then tell it to print x2, which would be my second iterate. So now my second iterate is -1.636 and so on. If I want to get the third iterate, well, then I could just do this. Change all the 1s to 2s, change the 2 to a 3, and have it export my third iterate like that. Of course, the third iterate is -1.530. How does that stack up with my visual? Yeah, so it looks like the actual 0 of this function is getting pretty close to that -1.53. So it seems to be working here. If I wanted a high degree of accuracy and I didn't want to keep repeating that line and manually typing in something different, adding more lines by hand, one thing I could do in programming is to do this. I could type in import numpy, which is, numpy is a numeric Python library. The reason I'm doing that is so I can set x equal to a vector. And this vector is going to have 10 entries in it. And I want all of the entries in my vector to start out as a 0 when I get to line 9 in my code here. The next thing I'm going to do is start using vector notation or array notation for Python. So I'm going to put a little bracket around that 0. So this is saying in my x array, I'm looking for the element 0 of my x array. An array is just a list in Python. You know, vectors are kind of just like lists of numbers in mathematics. And so this should work. Then the next thing I'm going to say is for n in range 1, 10, colon, and then I indent, and I say xn is equal to xn minus 1 minus fun evaluated at xn minus 1 divided by fun prime evaluated at x n minus 1. And so that, I think, maybe reminds you a little bit of the Newton's method formula, right? So if I say xn is equal to xn minus 1, well, I think I wrote the formula as xn plus 1, but you know, I could rewrite this formula maybe in a different way, but it would mean the same thing, right? If I changed that to n and I changed this to n minus 1, and this of course would be subscript n minus 1, n minus 1. So again, what I've done is I've just implemented the Newton's method formula, and now I'm storing the whole sequence of iterates in this x array in Python. And then what I'll have my function do at the end here is I'll have it print or export the whole x array into my console. So if I've done everything correctly and I hit, you know, the green play button up here, let me save it first and then hit the green play button, we'll see what happens. What happens with this for loop is it's going to loop and repeat that same line of code, but it's going to allow the variable n to take on all of the integer values between 1 and 9. I know it says 1 and 10, but that's not really how it works. Python stops 1 less than the end of the range. So n is going to take on the values 1, 2, 3, 4, 5, 6, 7, 8, 9. I started off by saying the 0th entry in x is going to be -1, so there it is over here in my console. And then the next iterates are -2, -1.6, -1.5, and then you can see Newton's method is closing in and getting closer and closer and closer. In fact, so close that I can't even tell the difference in these last 5 iterates unless I had more, more decimals displayed here than it's currently showing to me. But you can see this is going to be the first 10 iterates of Newton's method, starting from this initial iterate of -1 on this polynomial. Okay, so that's already a pretty decent and very useful code. But there's one thing we might do to make this a little bit fancier. And this is something you would want to do in practice if you were practicing applied computational mathematics. Is one thing you might do is say, well, I want to achieve a certain number of significant figures. I want my final answer to have enough accuracy to guarantee me I can write 4 significant figures in my answer, and all 4 of them will be accurate. My answer will be precise to at least 4 significant figures. And to achieve this, what we're going to do is we're going to define some way of determining error, and just follow along and see if this makes sense. If I want to define the error in some iterate xn, I'm going to start by taking the absolute value of the difference between xn and xn minus 1. What is that telling us? Right now it's telling us how much is my iterate changing from the previous iterate. Because if Newton's method really has closed in on a good solution, then it's not going to be changing very much from one iterate to the next. You notice back over here in my console, I'm going from -1 to -2. That's a really heckin' big jump. But then as I'm getting closer and closer to my real zero of my function, these iterates are barely changing at all. So that's something that I would like to be small. That could be included in my error sort of quantification. So I'll let that be one term. Another thing I want is I want this last iterate to actually be a zero of my function. And so I'm also going to throw in the absolute value of my function evaluated at the xin. And so if this really is a zero of my function, then this term should be very close to 0 for a very precise iterate. So now that I've quantified my error, what I'm going to say is I only have a certain tolerance for error. And what should my tolerance for error be? I think it should be 0.5 times 10 to the power minus the number of significant figures. I say that because if my error was less than 0.5 times 10 to the power negative number of sig figs, then whatever the error is, as I round off to just 4 significant figures in my answer, then any error is going to get rounded away as well. The error will be small enough, as long as the error is less than my tolerance, that I will achieve 4 significant figures of precision. And if that doesn't make sense to you, maybe sit with it for a moment. To get this to happen, I can't use a for loop. What I need to use instead is a while loop, which says repeat these 2 lines of code while my error is greater than my tolerance. So now again, no longer a for loop, but now we call it a while loop. To get this loop started, I can't have error be 0, because 0 would be less than my tolerance. So instead, I have to artificially set my error as the number 1, just to get this loop kicked off and going in the right direction. Now, with my for loop, I was having the loop iterate 10 times, and I set up this array to be size 10, because I was only expecting 10 iterates. But now, depending on how close I want my tolerance to be, or in other words, how many significant figures I want my answer, I might actually need more than 10 entries in my sequence of iterates. And so to make that happen, I'm going to set this to 1 instead of 10, which might sound counterintuitive, but then what I'm going to do on each iteration is I'm actually going to append a brand new what do you call it? I'm going to append a brand new entry onto my I'm going to append a brand new entry onto my array here using this numpy.append function. And you can Google that if you want to see the syntax. But all it requires me to do is put the previous array in, a comma, and then the new entry I want to put on. So the new entry that I want to append to this array each time I execute this loop is, of course, just the Newton's method formula. The last thing I need to do now, since I'm no longer using a for loop, is I have to explicitly tell the program to add 1 to this in index, so that continues to increase on each iteration of this while loop. Now, I'm just looking this over, and it seems to be everything fine, but I also need to say n is equal to 1 to start it off, and that gets rid of my errors. And now we are ready to hit go. And this is the same result as I got before with my for loop. I hope you'll agree. The difference between this output and my previous output is my previous output had 10 entries, because in my for loop I said I needed to have 10 entries. But this one actually cuts off the calculation after 1, 2, 3, 4, 5, 6, 7. After 7 iterates, it's determined that we're good enough. Which means after 7 iterates, I have enough confidence to say that these first 4 significant figures are really accurate. I know that this answer, the final iterate, is accurate to 4 significant figures. Okay, what if I wanted to be pretty confident that my answer is accurate up to 6 significant figures? Well, then I just have to change that line, hit play, and it looks like also even 7 iterates is good for 6 significant figures. What about 8 significant figures? Let's see if that... No. Huh. I'm actually starting to question. Okay, so at 10 significant figures, then it actually requires 8 iterates. So that just goes to show you that Newton's method is pretty slick for getting good accuracy with just not that many iterates. I'm actually kind of surprised by how accurate that gets so quickly. But in this new setup, in this new script that I've written, the benefit is that the program gives me the confidence to know that my final answer has the precision that I need, and it avoids doing any unnecessary calculations. Of course, this program executes very quickly because this is a very simple problem, but if you were going to continue to practice computational and applied mathematics, this concept of only iterating to get to the level of error tolerance that you want, or the level of precision that you want, and then stopping, that actually becomes important because you'll have more and more complex problems that require more and more computer time and resources to devote. So you actually want to minimize the calculation time in a lot of scenarios. Okay, is there anything else fancier we can do? The answer is yes. This video is not quite over yet because my code only works for a specific polynomial. This code that I've written only works for the polynomial x cubed minus x plus 2. But what if I want it to work not only for that polynomial, what if I want it to work for any polynomial? This is actually very doable. And to explain how that's doable, I have to kind of show you a certain one-to-one map between polynomials and vectors. So this is the polynomial that I had. Let's kind of show you this again. It's x cubed minus x plus 2. I could rewrite this polynomial like this. Let me write the constant first, and then write minus x, and then plus x cubed. So I've just reversed the order of this polynomial. So now the powers of x are in increasing order. And you could think of this too as 2 times x to the 0 power, right? X to the 0 power is just 1. You can think of this x as 1x to the 1 power. You could also think of this as plus 0x squared. Instead of minus x to the 1, you can think of it as plus a negative 1 x to the 1 power. And then you could think of this as 1x to the 3 power. Okay? Maybe you see where I'm going with this, but I can define a one-to-one map between this polynomial and the vector 2, negative 1, 0, 1. So this is just a vector, or an array, you could say. This is just an array where the entries in the array represent the coefficients in this polynomial. So if you see this array, what it represents is this polynomial. Let's do another example. Like what if I have, x to the 5th minus 7x to the 4th plus 3x squared plus 1. The array that I would map that to would be 1, 0, 3, 0, negative 7, 1. I hope that makes sense. We are going to use this one-to-one map between polynomials and vectors to write us a Python script that works for any polynomial. And this is the way that it's going to look. I'm going to start off by defining an array P, and P is going to be 2, -1, 0, 1. In other words, this is the array representing the polynomial that I've already been doing Newton's method to in this video so far. Now, to make this function be a little bit more general, I'm going to allow one of the inputs to this Python function be that polynomial P, or that array P of the coefficients of my polynomial. And I'm going to have to now define this a little bit differently. I'm going to come up with a new variable named result. I'm going to do another for loop. This time it's going to allow the index variable n to go anywhere between 0 and the length of p. So len p tells me how many entries are in my polynomial array. So len p would be 4 in this case, but not every vector will have length 4. Like this one over here had length of 6, right? There's 6 entries over here. Okay, so in this for loop, what we need is to add to the result the coefficient Pn times x to the power n. And then what we'll return is whatever that result is after I add up all of the terms in my polynomial. If that doesn't make sense to you right away, pause the video before you go on and really try to make that make sense to you. That's important here. Now, to get the derivative of this generic polynomial, I'm going to have somewhat of a similar situation. Where I have the same for loop that's going to go through all of the terms in my polynomial, except this time, what I'm adding to my result each time is not just the coefficient of the polynomial times x to the power n, but instead it's going to be x to the power n minus 1, because that's the derivative power rule, times n, because again that's part of the derivative power rule. So it would be hard, maybe not impossible, but it would certainly be very difficult to write a Newton's method function in Python that could work with just any old function, right? With sines and cosines and tangents and exponents and logarithms and whatever. But as long as we're sticking to polynomials, it's not too bad. It's actually pretty easy. And I think that even if you were doing rational functions, it wouldn't be too bad. I'm not going to do that in this video in case it takes me a while. But I know that it would be possible to do with rational functions. And maybe just to challenge yourself, maybe after this video, sit down and think, how would I do this with rational functions? And can I open up Python and also code the same sort of deal, but with rational functions? You know, for defining a rational function, you would actually need probably 2 arrays, one for the numerator polynomial and one for the denominator polynomial. And then you have to work out some kinks there. But, you know, definitely not impossible. I believe that some of you guys are definitely keen and apt to do so. So if you have time, maybe try that out. That could be like a little extra credit project. But moving on now for the different changes that I would need to make to this code, it's not actually that much. All I really have to do in addition is each time I call my function, I have to do comma p so that I can tell the function what polynomial we're executing with. And again, for fun prime, I also have to do comma p. So hopefully in this video you've gotten a good look at this code, enough to like copy it yourself line by line into Python. My intent is not to hide any of this code from you, although I'm not just going to send you the code in an email, because I do want you to get the practice of actually typing this out yourself in like a code editor. I've said before that your project in this class, in this Calculus 3 class, oh, I thought I did that. Just not in the right spot. I've said in this before, in this Calculus 3 class, your project can be completed with either MATLAB or Python or Visual Basic, and it doesn't matter. Earlier I gave you a Visual Basic code for Gaussian elimination, and now I'm showing you a Python code for Newton's method. Really, I feel most comfortable using either Python or Visual Basic. You could also use MATLAB. MATLAB Online is free to use, and I will gladly help you regardless of which coding language you choose to use. Python is also free, but it takes a little bit of a download and it's maybe a little bit tricky to install. But in any case, if you have any trouble downloading or accessing any place to code, let me know. And if you have any trouble coding and actually writing this code, let me know. Like if you're trying to translate what I've done here into Visual Basic or translate it into MATLAB code, the only small differences are in syntax, but you can overcome those usually with Google searches and usually with a little bit of help from a friend. Now what I've done is I've clicked play, and I think you'll agree with me when I say that this output is just the same as it was before, and of course that's because the polynomial array is representing that cubic polynomial that we were doing all along. But what if I want to try a different polynomial like this one? Maybe I want to try this 5th degree polynomial. So I type in 1, 0, 3, 0, negative 7, 1. Let's see if it works for that. Did I copy that correctly? No, 0, negative 7, 1. Okay. So now again, this polynomial array represents that 5th degree polynomial, and I'm a little bit nervous because I said this in a previous video, but Newton's method doesn't always work, and so maybe before I do this, I'm just going to verify that Newton's method will work on this, because I'm just being extra careful. Hopefully this won't take too long. I just got to type it in Desmos. So, yeah, it looks like, well, let me show you actually what I'm doing. I'll show you the visual. And like I said, I knew that there was some, like that initial iterate of x equals 0. That's not going to work. That's going to shoot us off towards negative infinity. Some of these are more problematic than others. What if we start with an initial iterate of x equals negative 5? And we'll have Python try to find us this 0 of my function whenever I start x equals negative 5. Okay. So here's my initial iterate. I'm changing it to negative 0.5. I think I said negative 5, but I meant negative 0.5. Just make sure that's right. Yeah. Okay. Negative 0.5 is now my initial iterate, and we've typed in my new 5th degree polynomial array, and we try it. And it turns out to get 6 significant figures of accuracy, 6 significant figures of precision. We needed 11. We needed 11 iterates in my sequence of iterates to converge to that 0 at negative 0.77. And visually, negative 0.77, that's about where that 0 is. So that checks out to me. And that, friends, is how you write a Newton's method Python code that works for just any old polynomial, as long as you type in the coefficients of the polynomial in a certain way. You can get it to any accuracy you want. Like if I wanted, let's say I got really greedy, and for whatever crazy reason I wanted 12 significant figures of accuracy. Of course, that makes my error tolerance smaller. That means I have to do just a few more iterations to guarantee that this number, this result, has 12 significant figures of precision. But all in all, seems to be working out. What would happen then if I chose a bad initial iterate? Like, what happens if I choose initial iterate 0? And as you can see on Desmos, that just flings it way out there and, like, you know, breaks the whole scheme. Well, if I chose initial iterate 0, I would probably have to cut off this code because it's probably going to kind of crash on me. Let's see what this looks like if I hit run right now. Okay, sure enough, all it says is runtime warning, divide by 0. Yeah, so not ideal to divide by 0. Another thing you could do to sort of handle those cases where it just blows up and it runs out of space is you could throw in a little if statement and says if n is equal to 100, or maybe just 20 is more likely. You could have it print some message like did not converge after 20 iterations, and then you can have it exit the while loop. Okay. So let me, if you're using an if statement like in conditional, you have to do 2 equal signs. And then, oh, I thought exit while was how it's done. Let me figure out the correct Python syntax for that. Well, maybe the better way to do this is to say while error is greater than tolerance and n is less than 20. And then I'm going to move this outside of the while loop and then say, okay, if n was 20, and that's the reason why my while loop stopped, because it no longer meets that condition, then I can say did not converge after 20 iterations, and yeah, that'd just be a good little note to leave yourself. So now let's find a polynomial that would not converge after 20 iterations. And I think maybe this is a good candidate, right? Because if you did this one, you can get into that loop that I talked about in the previous video where you jump from 0 to 1 to 0 to 1 to 0 to 1. And so I need to type in 2, negative 2, 0, 1, 2, negative 2, 0, 1. And my initial iterate could be either a 0 or a 1. Right now my initial iterate is a 0. So let's go ahead and try that. Huh. That's weird because it shouldn't be having to divide by 0. Let me again investigate this. You know, I think I found the source of the error. I think for the derivative it would be better to have this for loop start with a 1 instead of a 0, because the 0 term of the polynomial, the constant term of the polynomial, doesn't matter to the sum anyways when we're talking about the derivative, because in the derivative the constant term goes to 0. So instead of just starting with a 0 like I did before, now I'm going to start with the 1, or the x to the power 1 term in the polynomial as I'm executing this derivative function. That's the only change I've made to the code, and now if I do it, aha, there we go. Now I've got my sequence of iterates 0, 1, 0, 1, 0, 1, 0, 1, and my nice message that says it does not converge after 20 iterations. Now let's try the same function. Just move it to a place where it will converge, like, how about we do negative 1. That eventually converges. So I change my initial iterate to negative 1 and go in perfect. Okay. I think that's it for this video. I've showed you about the most sophisticated code you could hope for a Newton's method solver. I'll see you guys in the next video.